I won't have time to talk about Krylov methods. These are another class of very popular iterative methods. But the Krylov methods are, I'm just going to say a little bit about it. So Krylov methods are pretty different in philosophy from Gauss-Seidel and Jacobi. So they basically start with the x0, and you compute my a times x0, my a squared times x0, and etc. a to the kth power times x0. Basically, by computing this, and then you multiply a with this to get this, and then you multiply a with this to get the next one, right? So you get a series of vectors. And the span of these vectors, or the space of the linear combination of these vectors, is what's called the Krylov subspace. And the Krylov subspace method is basically looking for an approximate solution to the linear system within that space. So, for example, the most general, or one of the most popular Krylov subspace method, if you don't know anything about the matrix, is GMRS. Right, so GMRS is called the general minimized residual generalized GMRS, generalized the minimum residual something, right? So what it does is that it constructs this subspace and look for what is the vector in that subspace that minimizes the residual. It's kind of doing finite element in the discrete space, right? So these vectors are like my basis functions, the linear combination of which forms the entire Krylov subspace. And then you are looking for what is the C0 times x0 plus C1 times ax0 plus etc. plus ck times ak of x0, so that it minimizes the residual. So a times this minus b is minimized. Okay, I need to solve, so if k is small, I need to solve a small matrix system that is k by k to figure out what is the appropriate case to compute that minimum residual solution. And then this is basically my xk. Right? The idea is exactly that. So numerically, if you just directly do that, especially for ill-conditioned A's, you get some numerical instability. So there are procedures of how do you do that with an algorithm that is insensitive to round-off errors in computers. But like if you have exact precision floating points, just doing this minimization is exactly what GMRS does. So, and if you know more about the structure of the matrix, for example, if you know A is symmetric or even symmetric definite, there are better methods that doesn't require you to actually store all of these basis functions, like conjugate gradient and biconjugate gradient. They allow you to have much less memory than k vectors in the when you're solving this. So that's kind of a Krylov methods in a nutshell.